All right, so what we're doing today is we're going to start a new chapter that is about simple harmonic motion and oscillation. Now, in the lab, you already did the experiment that you had a spring and you put mass on the spring and you pull it down, and then because the spring provide a spring force, so there's oscillation, right? So the oscillation is up and down and up and down. And the task of your experiment was that to find the period of the oscillation. So you can see that. What is the oscillation? Oscillation is basically you have something that oscillates, and then there's what we call the simple harmonic motion. And the simple harmonic motion, we use SHM to indicate that's simple harmonic motion. So that's say you can do it vertically, or this is a spring, and you have a mass, and you just put it down. It's just going to offset. Like up and down, up and down. Or you can have a horizontal motion that you have the spring. Say this is the wall and this is the floor, and you have the spring attached to a block, and the block is oscillate, back and forth, up and down, and so forth. Okay, so this is what we call the simple harmonic motion. It repeats its motion at a regular interval. So with that, with that definition, we know that there's the period, the time that it takes for it to repeat its motion. So what is the period? Is what we're interested to find out. How fast does it oscillate, and what is the amplitude that that it oscillates, or the displacement, and what is the acceleration? So all these quantities, all the things that we are interested to find out for simple harmonic motions when you have a spring that oscillate up and down or back and forth. Okay, so there are because let's say this is a reference point and just go up and down. So you can see that there is a maximum amplitude that you can achieve. So this is what we call the XM, which is the maximum displacement, and we call that amplitude. Okay, so the maximum displacement is what we call amplitude. So how do we describe? How do we describe the motion of the block that's going in this direction? So what we found is that it actually follows a sinusoidal form, and we can actually describe this the motion of the block on the string as a function of time. So this is x of t, which means that the displacement, your x, remember, it is a displacement. So the displacement as a function of time can be described by this equation. This is xm, which is the amplitude. Okay, so displacement amplitude, and then times the cosine. Like I say, it can be described by a sinusoidal form. So you have your cosine, and then you have your omega t plus phi. Okay, so we need to, let's look at this equation. This basically tells you at any given time where the position of the block would be. So x of t is equal to a constant, the amplitude, and then times cosine of omega t plus phi. So we know that cosine of something, the maximum and the minimum value is plus or minus 1. That's the maximum value for cosine value, right? So in other words, the position, if you take this as a reference point, the position at the top, that will be your xm, and the position at the of the bottom, that will be negative xm, because your cosine, oscillate between positive and negative 1. Okay, so let's look at this. This most of the time, this is what we call the amplitude. Most of the time, it is a constant. What is omega? What's omega? We learned of omega before, right? When you have angular frequency, right? But at that time in chapter 11 and chapter 10 and chapter 11, when we learned omega, we learned it as angular velocity. So in this case, this is what we call the angular frequency. It's the same content, but it just applied to the simple harmonic motion in this when it's multiplied by the time. T here is the time. Then we call that angular frequency. Okay, so omega is angular frequency, and we actually already know that angular frequency and period, they are related by, how are they related to each other? Omega and t. 2 pi over t, exactly. So this is how you relate. I'm not going to derive it, but basically it just, if you have the period, then you can calculate angular frequency of simple harmonic motion, which is just 2 pi over the period, okay? So t here is the time, which is the variable. So the time can run from 0, 1, 2, 3, and so forth. And this guy, v, is what we call the phase constant. So it basically is determined by the initial condition. Let's say your block may not start at the reference point. It may be starting at any other point. So in that case, how do we know that? It is basically determined by the phase constant within that within this argument. So the whole thing here, omega t plus v, that is what we call phase. So what is the phase of the simple harmonic motion is determined by whatever that's inside the argument. Okay? So your xm, as I mentioned, is displacement amplitude. That is the maximum value. And your x of t, this quantity, we call that displacement. And you can see that it is not a constant. It is a function of time. Okay? So this equation will be adequate enough to describe the simple harmonic motion, whether in this direction, oscillating in this direction, or oscillating in that direction. So you have all this, this one. So the angular frequency, we know that has units or radians per second. You still have that. Now, in addition to angular frequency, the other frequency that we that we use a lot is what we call the frequency. So angular frequency and frequency that are related by this. So let me just write down here. Oh, maybe I'll just write here. So omega is equal to 2 pi times this quantity. So this is what we call frequency. And it has a unit of hertz. And hertz is also, that's equal to 1 per second. Okay? It describes how many oscillations within a second. And this is basically what frequency means. How frequent is the oscillatory motion that that moves? So this is omega is equal to 2 pi f, and your omega is also equal to 2 pi over t. So in that case, when you relate to when you set this equal to 2 pi t, you'll find that your frequency and the period, they bear a simple relation like this. Okay, so frequency is equal to 1 over the period. Okay, so exactly what do I mean when you repeat it? So let's say if you follow the simple harmonic motion, and this is the x, the displacement, and this is as a function of time. When you graph it, let's say you have something like this. So you have this, and this, and this. So the period, just based on this diagram, position versus time, the period will be from this point to that point, because it repeats itself. So at this point, you have t1, let's say t1. At this point, it corresponds to time t2. Then the period will be t2 minus t1, just by looking at this graph. So this is what we call period. Okay? And also, if you follow from this point, and then go down to this point, it repeats itself. This is what we call wavelength. Okay? From the distance from this point to that point, that is what we call a wavelength. And then from this point to the reference point, this is our amplitude. Okay, so this is what we call the amplitude. Now, if you measure amplitude from peak to peak, we call that peak-to-peak amplitude. So just by, this is just the definition. Okay, so once we know how to describe simple harmonic motion using the sinusoidal form, we are ready to find out how fast is a block moving, because you have the displacement that's a function of time. And by definition, how do we find velocity? That's from chapter 2. What is the definition of velocity? Time rate of change of displacement, right? So if you remember, velocity from chapter 2 is equal to time rate of change of displacement. We now, in the past, we did not use it because a lot of times, you do not have to use that. But now for a simple harmonic motion, it repeats its motion in a regular time interval, and the simple harmonic motion can be described as a function of time. Then we are ready to actually utilize this expression to find out how fast is a simple harmonic motion of the system. So now your velocity, again, will be a function of time. So let's say velocity as a function of time is time rate of change of your position, displacement. So that just replace that displacement with the whole thing here. So you have your x of t now is equal to xm, and then cosine of omega t plus this quantity. Okay? So your xm is a constant. So it does not go, when you do the time, when you do the derivative, you can put it outside. And then what you have is ddt, and then you have omega t, and then plus this. So you have to, I'm sorry, I'm missing the cosine. The derivative of this thing. So what is the time derivative of this thing, of a cosine function? Have you done that in calculus? Huh? Negative sign. Are we missing anything? So we know that there's a negative sign, right? And the argument, the phase does not change. But then in addition to that, are we missing anything? Your time derivative of the omega t, huh? Okay. So we already know that d cosine, okay. How about let's put this. This is equal to what? Negative. What happened to this omega? Don't you have to like move it, like when you take the time derivative of t, whatever constant? Yeah? Yeah. Right? Uh-huh. Okay. So d of this is a constant in front of a t, so that has to be taken out because you differentiate with respect to t, and then the cosine becomes sine, and there's you have to have there's a change of sign. If you don't know, that's fine, but it is end result that we need to know. Okay. So what we have here is that, so now applying to this, you have negative omega xm, and then cosine becomes sine, and then you have your omega t plus this whole thing. Okay? So this describes velocity as a function of time, which is equal to negative omega times the displacement amplitude, and then times sine of omega t plus v. So we can see that, compare this equation to that expression. They all have the amplitude xm, but then this is a cosine, and that is sine. Okay? So now, we can also do the same thing. If we know the velocity as a function of time, we can actually find out the acceleration. What is the acceleration of the block? Right? Because acceleration is defined as what? What is the definition of acceleration? Exactly. Acceleration is time rate of change of velocity. So your A is defined as dv dt. Now, our velocity is a function of time. So we can just do the same thing. So you have your A of t, which is equal to d dt. And then that just copy down what the v of t is. Your v of t is negative omega xm. And then you have your sine omega t plus this. So again, these two things, omega and xm, they are constants, so you can move it outside the differentiation sign. So you have negative omega, and then you have your xm. You're just going to differentiate this. Take the derivative of this. So what would that be? When you d sine dt. D sine dt, that gives you, huh? What does that give you? D sine dt, omega times cosine, right? So sine becomes cosine. So now you have the omega, extra omega coming from there. So omega times omega, that becomes negative omega squared xm, and then cosine of omega t plus this. Okay, so this is the expression for the acceleration as a function of time. So you can see that just by describing the simple harmonic motion with the sinusoidal form, you can actually find out what the velocity expression would be, what the acceleration would be, and they are all dependent on they all depend on time. So in other words, they are not constant. They are changing. They are changing all the time because there's a time information, right here, the variables here. So let me just rewrite. So we cover velocity, amplitude, acceleration. So we seem to have, a very good handle about how the simple harmonic motion is because you know the position, you know the velocity, you also know the acceleration. So let me just rewrite it. Put all these three expressions side by, lay out together so that you can have a better better appreciations of how each parameters is related to each other. So, as we mentioned, x of t is equal to xm, and then you'll have the cosine of omega t plus this. V of t is equal to negative omega xm, and then sine of omega t plus this. And then for the acceleration, you have negative omega squared xm, and then cosine omega t plus this. So let's look at this three expression. This is displacement. This is velocity, and this is acceleration. So this guy xm is called the amplitude displacement. So anything that's in front of the sinusoidal form is what we consider as amplitude. So in that case, what is the amplitude for velocity? What will be the maximum value that the velocity can attain? That will be whatever that's in front of the sinusoidal form, because sine and cosine, they both vary from positive and negative 1. So the maximum value that this can have would just be 1 or negative 1. So the maximum amplitude for the velocity would just be whatever that's in front of it. So we call that velocity amplitude. And that so your xm would just be xm. That's the amplitude displacement amplitude. For velocity, we call that vm. That's the maximum value that the velocity can have, which is just omega times xm, okay? Or which is negative omega times xm. In fact, we can just drop the negative. Okay, let's just keep the negative, just so that we know that they are different by that. But then when there are times when you do calculations, you don't have to keep the negative sign. I'm keeping the negative sign here just to let you know that they are off by some. They are not in phase. They are actually in different phase. In other words, when I say in phase or out of phase, when something that's in phase, it means that they all reach the maximum at the same time or reach the minimum at the same time. This is a situation when we call that in phase. There are situations that one quantity reaches the maximum, the other quantity may not reach the maximum. This is called they are not in phase. And when one reaches the maximum, one reaches the minimum. This is called out of phase. 180 degrees out of phase. Okay. So you have your xm. You have your xm, that's that, and vm is equal to negative omega xm. Now let's look at acceleration. Acceleration also has an amplitude. Acceleration amplitude is simply equal to negative omega squared and then xm. So these are the things that you need to know. This relates how the amplitude of various quantities relate to each other. Velocity, once you know the angular frequency, if you know the angle, if you know the displacement, you can actually find out what the velocity amplitude is, and also likewise for the amplitude for the acceleration amplitude. Okay, so that's become very useful for that. Okay, and in fact, I think in the book. They just dropped that negative. So I'm just going to draw this. That, when you do problems, you don't have to include that negative sign. But then include that negative sign here just to let you know that they are not in phase. Yes? Okay, so I'm just saying that. So amplitude. So on this side, this is for the amplitude. These are all amplitude. And I'm just saying that, for the amplitude, this is just xm, so I'm just copy it down. But you don't have to copy it down. I'm just, give you some, lay them out side by side so you know what's going on. In fact, we can just remove that negative sign if we just work with the amplitude. Okay. Amplitude, we know that it's, they differ by positive and negative 1. So to avoid confusion, let's just remove that negative sign. But, so this, you don't have to include that. That will be fine. So you'll be just like this. So xm would just be xm. I'm just copy it down to make it more look regular. Okay. All right. So what we have here now, let's compare this expression and that expression and see what we get. This expression is xm times cosine of something, and this one is negative omega square xm times something. So this is your x of t. So your acceleration as a function of time is actually equal to negative omega square and then x of t. Okay, so you can see that your acceleration and displacement, they bear a very simple relation, which is just subject to a negative omega square. Okay. So when we look at this, we can actually graph them and see what they look like. So let's say again, let's say position versus time. So if I have the graph like this, or I can have a graph, let's say like this, the maximum, and then zero displacement, and then minimum, and then maximum. So these are the points that have zero displacement. These are the points that have the largest displacement. Okay. As we mentioned, from this point to that point, that's your xm, the amplitude. And these are points that does not have any displacement at all. Now, if we look at how the velocity changes with time, then this is basically what we get. When the amplitude gets the largest, when the amplitude of displacement gets the largest, there's no velocity. Okay, and when you have this, when you don't have a displacement, you actually got a largest, the velocity amplitude, although it's negative sign. And then so likewise, you have something that's zero. When this is zero displacement, you have the maximum amplitude. Let's say right here. And then when you have the maximum amplitude, you have zero velocity. So this is the graph for velocity. So that would be something like this. So the key point here is that when you have the largest amplitude, you have zero velocity. V equals to 0 here. And when you have zero displacement, you have the largest amplitude. Okay, so this basically describes how the simple harmonic motion is. Remember, why is it important? Because the displacement is actually indications of how much energy is stored in the spring potential energy, and the velocity actually give you an indication how much kinetic energy that the system has. So when you have a situation that you have the maximum amplitude, you have zero velocity, it just means that all the energy will actually be in the form of a spring potential energy and zero kinetic energy. When you have a situation at this point, when you have zero displacement, which means that zero spring potential energy, but you have the largest velocity, which means that largest kinetic energy. Okay, so that that basically tells you that they are 90 degrees out of phase. When this reach maximum, this gives you 0. When this reach 0, this reach negative maximum, and so forth. Okay, so this is when you're dealing with the graphing the velocity as a function of time. We can also graph the acceleration as a function of time, and we notice that the acceleration and displacement, they are related by this. So they related by a negative sign, which means that they're 180 degrees out of phase. Okay, so what you have here is that when you have a maximum amplitude, you would expect the acceleration will also have the maximum value, but it is negative. This is positive. When this is positive, your acceleration is negative, and that they both have the maximum value. So let's say the maximum AM is right here. It's negative. And then, so when you have zero displacement, you have no acceleration. When you have the largest amplitude, you have the largest acceleration. When you have zero displacement, no acceleration, largest amplitude, then you have the largest acceleration. So your graph will be like this. Am I missing something? Let me see. 0.0. Wait. So this one, when this is negative, this should be positive. Sorry. Positive, so let's say somewhere here. It's positive, and that should be negative. So you'll have a graph that's look like this for the acceleration. Okay? Maximum amplitude, maximum acceleration, zero displacement, zero acceleration, and so forth. So that basically what we graph here is based on the sinusoidal behavior of the of the simple harmonic motion. Okay. So what can we learn from this? As I mentioned, the whole interplay, the interchange between kinetic and potential are determined by the displacement and also velocity. When you have the largest velocity, it means that all the energy is in the form of kinetic energy. When you have the largest displacement, all the energy will be in the form of spring potential energy. Okay, so let's look at. In addition to that, let's look at when you have a simple harmonic motion. Let's say you have the block that is attached to the spring. So the spring has a spring constant, and there's a spring force acting on the block. So in that case, let's look at the what we have here. So you have the spring attached to the block. This has a spring constant, and this is spring constant, not the kinetic energy. So you have spring constant K, okay, and you want to find out. So let's say there is a force. There is a force which is a spring force by Hooke's law. What would that be? And the position of is a function of position. So what would that be? That will be negative kx, right? So now because this thing is oscillating, when it's oscillating, your x is no longer a constant. Your x now, when it's executing as a simple harmonic motion, your x is actually a function of time. So what we have here is that you actually have this. So it's, instead of just negative kx, it's actually negative k of t, okay? And we have this x of t that is in that expression, okay? So keep that in mind. And we also know that force is equal, by Newton's second law, force is equal to ma. So that is also equal to ma. And again, your acceleration is no longer a constant value. It is now a function of time for simple harmonic motion. And we also have that expressions laid out right here. So what you have here is this. So you have the force, which is equal to negative k of kx. That's equal to ma. Okay. So now, what do we do with this information? So what we have here is that we already know that acceleration and displacement, they are equal to this. So what we're going to do is that we can replace this acceleration by this expression and see what we get. Okay, so what we have here is that you have negative k x of t that's equal to your mass of the block, and then a of t that's equal to negative omega squared, and then x of t. So what we have here is that your x of t, they just cancel each other because they appear on both sides of the equation. So what we have here is that you have negative, negative, they cancel each other as well. So what we have here is that your k, the spring constant, not the kinetic energy, the spring constant is equal to mass times omega squared. Okay? And this equation becomes very useful whenever you want to calculate other quantity, because this information gives you the value of the angular frequency. So let me just write it down again. So omega squared is equal to k over m. So how fast would this simple harmonic motion repeat itself really depends on the mass of the block and elasticity of the spring constant. Okay. So you have your omega. The expression that you sing a lot of time will be omega is equal to square root of k over m. And if you remember, your omega is equal to 2 pi over t. So your period is equal to 2 pi and then square root of n over k. And this is actually the expression that you use to study to find the period in lab 11. If you recall, that's 2 pi square root of n over k. Okay, so that's basically tells you that you can actually all these quantities are related to each other. Okay, any questions so far? No questions? I'm actually going to stop it right now.